Section 12.5, Equations of Lines and Planes. The vector equation of a line through the point x0, y0, z0 is r equals r0 plus tv, where r0 is the position vector of x0, y0, z0, and v is a vector parallel to the line, and t is a scalar. Parametric equations for a line through the point and parallel to the direction vector are then x equals x0 plus at, y equals y0 plus bt, and z equals z0 plus ct. So what we're saying over here is that you take some point and you draw some position vector that points to that point, and then this point lies in some line. So we want to find an equation for that line. So what you do is you take a vector and you point to another point in the line, and you point to another point in the line, and you point to another point, and you point to another point, and you keep pointing to all of these different points using different vectors until you build up the entire line. So the question is, what is a formula for that arbitrary vector that points to an arbitrary point in the line? Well, you do it by taking that initial position vector that you have, r0, and you take a vector, v, that's parallel to the line, and then you just add them together. So you have this vector pointing to this vector, and then when you add them, you get a vector that points to a point. So you keep scaling v so that it points to different points when you add them together. Remember that vectors have no position, so I could just move v up to the line, no problem. Okay, let's find a vector equation and parametric equations for the line that passes at the point 5, 1, 3 and is parallel to the vector I plus 4j minus 2k. So what we can do is write r0 as our position vector through our point 5, 1, 3, so that's just 5, 1, 3. And in IJK notation, that's 5i plus j plus 3k. And how about v? Well, vector v parallel to the line is just I plus 4j minus 2k, because they gave it to us. So building up the equation for r, we have r equals r0, which is 5i plus j plus 3k, and that's plus t times v, so that's t times I plus 4j minus 2k. So we can group together our I, j, and k's, so we can get another equation for r as 5 plus t times I, so that'll be the ith component of r, and then 1 plus 4t j, and 3 minus 2tk. So then if we want parametric equations, that would just be x equals 5 plus t, y equals 1 plus 4t, and z equals 3 minus 2t. All right, how about two other points in the line? Well, we can do this by just plugging in different values of t. So how about we plug in some easy ones like t equals 1? Well, if we plug in t equals 1, then we get x equals 6, y equals 5, and z equals 1. So the point 6, 5, 1 is on the line. If we plug in another value of t, how about minus 1? Then we get x equals 4, y equals negative 3, and z equals 5. So 4 minus 3, 5 is another point in the line. What we can also do is express the line using direction numbers for our parallel vector in the form of symmetric equations. So what we do is we eliminate the parameter t. So we take x equals x0 plus at, we subtract x0 divided by a, and that equals t. We subtract y naught divided by b for y, and that'll equal t, and then we do the same thing for z. Because they all equal t, that means that they all equal each other, and we've eliminated the parameter. As another example, let's find parametric equations and symmetric equations of the line that passes through these 2 points a and b. Notice in this case they did not give us the parallel vector v, so we'll have to construct it. What we can do is write that v equals the difference between these 2 points. A vector through 2 points is just, what you get by subtracting. So we'll take 3 minus 2 and minus 1 minus 4 and 1 minus minus 3. So that just equals 1 minus 5, 4. Then we need our point and direction numbers. So it looks like from our parallel vector, a equals 1, b equals minus 5, and c equals 4. And our point, how about we choose to just take a? So we'll make p naught equal to 2, 4, minus 3. Doesn't matter if we start with a or b. So this means we'll have x equals 2 plus t, y equals 4 minus 5t, and z equals negative 3 plus 4t. So those are our parametric equations. If we want symmetric equations, we just solve for t. So that means it's x minus 2 over 1 equals y minus 4 over minus 5 and z plus 3 over 4. And those are our symmetric equations. Let's see at what point does this line intersect the xy plane. Well, if it intersects the xy plane, it's like on ground level when z equals 0. So we can take z equals 0, and that'll imply that x minus 2 over 1 equals y minus 4 over minus 5 is equal to 0 plus 3 over 4, which is just 3 over 4. Okay, so now if I want, I can solve each of these separately. So x minus 2 over 1 equals 3 over 4. Well, solving that gives x equals 11 over 4. Just cross multiply. And then we can solve this guy over here, and we get that y is 1/4. So that means that our point is 11 over 4, 1/4, 0. What if we wanted a line segment though, and not an entire line? So we just want to start at R0 and stop at R1. Well, let's draw this really quick. We have a line L. We have some starting vector R0 pointing to some starting point. So here's R0. And we also have R1 where we're going to stop at. So there's R1. So it looks like if I took R1 and I subtracted R0, so that would be like drawing this thing over here, that's minus R0, then I would get this vector over here, which is parallel to my line. So what I can do is I can say that this parallel vector over here is v equals R1 minus R0. So I can build up an equation for R by saying that R equals R0 plus TV, but in this case I can say that V is equal to R1 minus R0. Then if I just start at t equals 0 and end at t equals 1, I'll only trace out the part between the R0 and R1. So I'll just get a line segment. So that's why we just go from 0 to 1. Notice we can turn this equation into this equation. by distributing t and then grouping together our t terms, because we get t, we get minus, we group together r naught terms, we get minus r naught times t. So we have r naught plus minus r naught times t. So factoring out r naught, we get 1 minus t times r naught, and then the tr1. Let's show that the lines L1 and L2 with these parametric equations are skew lines. So in order to show that they're skew, we have to show that they have no intersection points and that they're not parallel. Well, showing that they're not parallel is kind of easy, because if I look at the vectors 1, 3, minus 1, because those are the vectors parallel. Remember, A, B, C, that vector v times t is the vector parallel to the line. So in order for the lines to be parallel, the vector parallel to the line would have to be parallel. So I'm looking at 1, 3, minus 1, and I'm looking at 2, 1, 4. So notice that 1, 3, minus 1 and 2, 1, 4 are not parallel, because parallel vectors are scalar multiples of each other. And notice I could multiply this by 1. I can multiply that by 2 to get from 1 to 2, but multiplying that by 2 would not give me 1. So these guys are not parallel. So that means that L1 and L2 are not parallel. So we're halfway done. We still have to show that they also don't intersect. Notice this can't happen in 2 dimensions, but in 3 dimensions it's fully possible. So let's suppose they do intersect. So suppose L1 and L2 intersect. We'll show that this is impossible. Okay, so if they intersect, then there must exist some t and some s such that, looking at our first set of equations, remember, if they intersect, there's a point of intersection, so these guys must be equal. Similarly, these guys must be equal, and these guys must be equal, because we have to have a point where x equals x, y equals y, z equals z on both of them. So that means that we have to have a point where 1 plus t is equal to 2s, and where negative 2 plus 3t is equal to 3 plus s, and where 4 minus t is equal to 3 plus 4s. So if we solve the system with the top 2 equations, then we get that t equals 11 over 5 and s equals 8 over 5. So let's plug that into the bottom equation. Instead of 4 minus t, 4 minus 11 over 5. And that should equal negative 3 plus 4 times 8 over 5. So on the left we get 9 over 5. And on the right we get 17 over 5, which are not equal. So these guys are not equal. So that means that there is no solution to this system of equations. So there is no point of intersection. So this is a contradiction. So L1 and L2 must not intersect. So we've shown that they're not parallel and they don't have a point of intersection. So that implies that L1 and L2 are skew lines. How about equations of planes now? If we want to build up an equation of a plane, then what we can do is find some point, P0, which is x naught, y naught, z naught, then it has some position vector that points to it. And if I want to look at an arbitrary vector pointing to an arbitrary point in the plane, then I can call that vector r, which points to an arbitrary point x, y, z. So that means that r minus r naught is just a vector parallel to the plane. Just an arbitrary vector parallel to the plane that comes out of my point p naught. So then if I look at a vector that's normal to the plane, that means a vector coming out of the plane perpendicular to it, and I look at this arbitrary vector r minus r naught, they must be perpendicular to each other. So if they must be perpendicular to each other, that means that their dot product must be 0. So I can write the equation in the plane using that fact. It's all of the points that satisfy in there for r, where the dot product with the normal will be 0. So what we can do is distribute the dot product and get this other form, n dot r equals n dot r naught, either way. So that's a vector equation of a plane through the point x naught, y naught, z naught. And then we can also come up with a scalar equation of the plane. Notice that we'll put n as ABC for its components. And then r is x, y, z, r naught is x naught, y naught, z naught. So when we dot it, the ABC moves over to each of these things. So if I want, I can just write that as this over here in terms of each of the components. The A moves over to each of them. So you could distribute the A if you wanted to in the same fashion. Let's do an example by finding an equation of the plane through the point 2, 4, minus 1 with normal vector 2, 3, 4. So if the normal vector is 2, 3, 4, that means that's what our A, B, and C are. So A is 2, B is 3, and C is 4. We also have our initial point 2, 4, minus 1, so that's what our x naught, y naught, and z naught are. So we have 2, 4, and minus 1. So the equation for our plane is A, which is 2, times x minus x naught, which is also 2, and B times y minus y naught, so 3 times y minus 4, plus C, which is 4, times z minus z naught, which is 1, so minus 1, so minus 1 is plus 1. And that is equal to 0, because the dot product is equal to 0. So we can distribute and get 2x plus 3y plus 4z equals 12. Okay, let's find intercepts now. Well, if y and z are both 0, then that'll tell me what the x-intercept is. So the x-intercept must be 6. Just plugging in y and z 0. It's 2x equals 12. Similarly, if x and z are 0, then that'll give me the y-intercept of 4. And if x and y are 0, then that gives me the z-intercept of 3. So I can draw this plane kind of triangular because I can't draw an infinite, plane, so I'll just cut it off at a triangle. So it'll look something like this. Very roughly. So I'll put my z-axis over here. And my z-intercept I said was 0, 0, 3. My y-axis over here at 0, 4, 0. And then my x-axis over here at 6, 0, 0. And I'll draw what's going on behind it. So these are the axes behind the plane. And the plane slices through obviously infinitely in all of these directions, but I'll just draw the slice. Notice that what we did over here by distributing each of these coefficients, A, B, and C's, and transforming it into this equation over here, that's something we can always do. And if we move the 12 over to the other side, then we can always set it equal to 0. So in general, we can always rewrite the equation of a plane as what we call a linear equation, ax plus by plus cc plus d equals 0, where d is minus a times x naught plus b times y naught plus c times z naught. Because when you have your x naught, y naught, and z naught plugged in, those are all just numbers, and they can all just be incorporated into the constant d. So how about we find an equation of the plane that passes through the points p, q, and r. So in this case, we were not given the normal vector. So we're going to have to find the normal vector ourselves. So remember that the cross product gives us a vector perpendicular to two other vectors. So if we can just build two vectors in the plane, we can take the cross product, and that'll have to be perpendicular to the plane. So how about we write two vectors using our points? So we have a vector pq through the points pq, we'll get by subtracting. So 3 minus 1 is 2, minus 1 minus 3 is minus 4, and 6 minus 2 is 4. And then similarly, we can get vector PR as 4 minus 1 minus 2. So that means that our normal vector to our plane, PQ cross PR, is equal to I, J, K, 2 minus 4, 4, 4, minus 1, minus 2, where we take the determinant of this matrix. So if you take the determinant, you take the determinant of this times I, and then this times J with a minus sign, and then this times K, and you'll get 12I plus 20J plus 14K. So now we have our A, B, and C, 12, 20, and 14. Let's choose a point. It doesn't matter which point we choose to start at for our plane. So how about we just choose P132. So that means that we'll have 12 times x minus 1 plus 20 times y minus 3 plus 14 times z minus 2 equals 0, which is the same as 6x plus 10y plus 7z equals 50. How about we find the point at which the line of the parametric equations x, y, and z intersects this plane? Well, notice that if they intersect, then they have to share a common x, y, and z values. So that means I can replace this x, this y, and this z with the x, y's, and z's they gave me. So how about we do that real quick? We'll have 4 times, instead of x, 2 plus 3t. And then we'll have 5 times minus 4t. And then we'll have minus 2 times 5 plus t equals 18. So solving for t, we get that negative 10t must equal 20. So that means that t is equal to minus 2. So now we know what the value of t is. We can plug that back into our equations for x, y, and z, our parametric equations, and we can see what the point is. So x equals 2 plus 3 times minus 2, so that's 4. Y is negative 4 times negative 2, which is 8. And z is 5 minus 2, which is 3. So our point is negative 4, 8, 3 for our intersection. next up, we have two planes parallel if their normal vectors are parallel. If two planes are not parallel, then they intersect in a straight line, and the angle between the two planes is defined as the acute angle between the normal vectors. So if they intersect, that means that we get a line of intersection. In this case, this would be it, where they cross each other. And notice in that case, we've got one normal vector from our bottom plane, perpendicular to that plane, another normal vector perpendicular to our other plane, I guess you could call our top plane, and there will be an angle between those two guys. So we define that angle to be the angle between the two planes. So in order to find any angle between two planes, we just have to find the normal vectors. So let's do that in this example. The normal vector is just the a, b, and c from the equation of the plane. So the coefficients of x, y, and z. So our first normal is pretty easy to read off. It's just 1, 1, 1. Our second normal is the coefficients for the second equation of the plane, so that's 1, 2, 3. Or, sorry, there's a minus. Almost missed it. 1, minus 2, 3. Okay, so then we need to figure out what the angle between these two normal vectors are. Remember, we can calculate the angle between vectors using a dot product. We have a formula, the cosine of theta, where theta is the angle between the vectors, is the dot product of our vectors divided by their lengths. So what we'll do is we will plug in 1 dotted with 1, so it's 1 times 1 plus 1 times minus 2 plus 1 times 3. And then for the lengths of these guys, we've got the square root of 1 plus 1 plus 1, because each of those squared is still 1. And then the square root of 1 plus minus 2 squared is 4, plus 3 squared is 9. So simplifying, we get 2 over the square root of 42. So theta is the cosine inverse of this mess. So it's the cosine inverse of 2 over the square root of 42, which is about 72 degrees. Since our normal vectors are not parallel, that means that the planes intersect, so there is a line of intersection between them. If we can figure out a point on that, then we can find a vector parallel, and we can build up an equation of that line. So in order to find a point on this line, how about we just plug in some value of c, which will make this thing a little bit easier. So let's look for about when c is 0. So plugging that in, how about we plug that into this right over here and this right over here. So we get x plus y equals 1. And we get x minus 2y equals 1. So solving for x and y, we get x equals 1 and y equals 0. Because you just let x equals 1 minus y and plug that in, 1 minus y minus 2y, 1 cancels. You get y is 0, plug back in, you get x is 1. So that means that the point 1, 0, 0 is on L, the line of intersection. So now we just need a vector parallel to the line. That way we can build our equation. So we, well, remember that if we want a vector parallel to these two planes, then we want a vector that's perpendicular to both of the normal vectors, because the normal vectors are, each of the normal vectors is perpendicular to its plane. So if we have a vector that's perpendicular to each of those, it would have to be parallel to the plane. Well, remember, that's just the cross product. The cross product is perpendicular to both of the vectors you put in. So we'll take the cross product of our two normals. And that's just with ijk in our top row. 1, 1, 1 was our first normal, and 1, minus 2, 3 was our second. And taking that cross product gives you 5i minus 2j minus 3k. So now we have our a, b, and c for our parallel vector. Notice we use a, b, and c a little bit loosely depending on the context. If we're talking about a line, then a, b, and c refers to the components of our parallel vector v. If we're talking about a plane, then a, b, and c refers to the components of our normal vector. So we're talking about a line, so when I say a, b, and c, I mean these guys. So we'll have x minus x naught, which is, how about 1? It doesn't matter which point, but we chose 1, 0, 0. And we'll divide by a, so that's 5. Then y minus 0 is just y over minus 2, and z minus 0 is just z over minus 3. So those are symmetric equations for the line of intersection. How about a formula for the distance between a point and a plane? Let's see if we can build this. We need to start with some point on the plane. So how about we say that that's p naught. And it would be nice to see a vector that represents the distance from p naught to p1. So we'll call it the vector b. So that'll be the vector that goes from p naught to p1. We'll get that by subtracting. So we said p1 was x1, y1, z1. So subtracting from x naught, y naught, z naught, we have x1 minus x naught, y1 minus y naught, and z1 minus z naught. So let's see if we can use this to build the formula that we want. Let's draw a plane. Let's see what's going on. So let's say this is a plane. And here's my point on the plane p naught. And then here's my point floating somewhere else. I want the distance from over there. So I want to know how far it is from p naught to p1. I'm not going to use this distance over here from the vector I constructed though, because otherwise I would have a million different distances. If I chose a different p naught, then it would be shorter. Or if I chose this p naught, it would be longer. I want the shortest distance possible. That's what my distance between my point and my plane will be. So that means that I want to go perpendicular. So remember that the normal vector is perpendicular to the plane. So if I want this to be perpendicular, then I should be looking at normal vector n. However, the normal vector n, how about I use another color for that? So we could say that this is the normal vector n. That doesn't necessarily go all the way to p1. It could go past it. It could go a little bit before, like the way I drew it. It could go any length. So it points towards p1, but it doesn't necessarily represent the distance. The length of n won't necessarily be the distance. We want this entire distance d. So what we can do is we can use our vector b that we have, and we can project it down onto n. So by projecting b downwards, that will give this vector right over here, which will point from our plane to p1, and it'll have length d. So I want the scalar projection. So we can write n equal to ABC, and our distance will be the scalar projection, or the length of the scalar projection. Well, I don't know, not length, but the absolute value. In this case, it's a scalar, so it doesn't make sense for me to say length. So that's the component of b along n. The component is possible for it to be negative, so I need to take the absolute value. So that means I'm taking the absolute value of n dotted with b over n when I take the length. So this is a length, this is an absolute value. And that's just the absolute value of, well, n dotted with b is a times x1 minus x naught plus b times y1 minus y naught plus c times z1 minus z naught. And then the length of n is just the square root of a squared plus b squared plus c squared. Okay, how about we distribute each of our coefficients? So we get a times x1 plus b times y1 plus c times z1 minus a times x naught plus b times y naught plus c times z naught, all over the square root of a squared plus b squared plus c squared. However, remember that this minus ax naught plus b naught plus c z naught is just d, because it's x naught, y naught, z naught is a point in the plane. Remember that we said that when we write an equation in this form with a d in it, then d is just minus that, which is exactly what we have in there. So let's substitute d in for that. So we can write the absolute value of ax1 plus by1 plus cz1 plus d, all over the square root of a squared plus b squared plus c squared. And now we have a formula for the distance from a point to a plane. So let's use our formula. Notice that in this case we want the distance between parallel planes. We have a formula for the distance from a point to a plane, but not the distance between two planes. But if we want the distance between two planes, how about we just find a point on the plane and then find the distance from that point to the other plane? So to do that, how about we set y and z to be 0. So that'll tell us what the x-intercept of that plane is. So that means that 10x equals 5. So x is equal to 1/2. I did that for this first plane. So that means that the point 1/2, 0, 0 is on the plane 10x plus 2y minus 2z equals 5. So let's get the distance between that and our other plane, 5x plus y minus c equals 1. So the distance will be a, b, and c for that plane. Notice that those are just the coefficients, a, b, and c. So that's 5, 1, and minus 1. So we have 5 times our point x1, so that's 5 times 1/2, plus 1 times 0, minus 1 times 0, and then minus d, which is 1. Well, in this case, d is on the wrong side. You have to move it over to figure out what d is. When you move it over, you see that minus 1 equals d. Okay, we divide by the square root of a squared plus b squared plus c squared, so that's 5 squared plus 1 squared plus minus 1 squared. So that gives us 3 over 2 on the top, and it gives us 3 rad 3 on the bottom. So that's just rad 3 over 6 as the distance between our two planes. Previously, we showed that these lines L1 and L2 are skew lines. So that means that I could put each of the lines in a plane, and those planes would be parallel to each other. So that means there's a distance between those two parallel planes, and we could find that the same way we did in the previous example. So how about we say that the plane that line L1 is in P1 and the other line be in P2, and those are parallel planes. The vector V1 parallel to the line L1 we've seen is 1, 3, minus 1. It's just the A, B, and C for the line. So 1, 3, minus 1. And then for our other parallel vector V2, it's just the coefficients on S, so that's 2, 1, and 4. So I want a equation for one of these planes. So how about I get an equation for the second one, P2? Well, I need a normal vector n for P2. And our normal vector will have to be perpendicular to the vectors that are parallel to the lines. So it must be the cross product of those two. So I'll take the cross product of V1 and V2. So that means that it'll be the determinant of this matrix with I, j, and k, and 1, 3, minus 1, 2, 1, 4. So that's 13i minus 6j minus 5k. Okay, so now we have a normal vector. We need a point on our plane P2. How about we set s equal to 0? That'll give us the point 0, 3, minus 3 on line L2, so that'll be on plane P2. So that means that an equation of the plane is 13 times x minus 0 minus 6 times y minus 3 minus 5 times z plus 3 equals 0, which is the same as 13x minus 6y minus 5z plus 3 equals 0. So that's the equation for P2, or that's an equation for P2. I want the distance between that and P1, so I need a point on P1. So how about we set t equals 0 to get a point on P1? Well, that'll mean that 1 minus 2, 4 is on P1 just by plugging t equals 0 into L1. So now I have a point, I have a plane, I can find the distance between them. So we'll say the distance d is equal to the absolute value of 13 times 1 minus 6 times minus 2 minus 5 times 4 plus 3 over the square root of 13 squared plus negative 6 squared plus negative 5 squared, which is 8 over square root of 230, which is about 0.53.